The displacement current. Now let's consider the process of charging a capacitor. A current I is present on the wires but not in between the plates, so we will have charge buildup. So plus Q charge is building on this plate, minus Q charge is building on this plate due to this current. If I write basically Ampere's law, the closed path integral B dot ds for this Amperian loop S1, I see that this is mu 0 times the current enclosed by this loop. The current enclosed by this loop is I, so this is going to be equal to mu 0 I. That's because according to Ampere's law, the closed path integral B ds is mu 0 I enclosed, where I is the total current through any surface bounded by the path P. So this is the path P. Now this is basically considering a closed surface that is on this side of the path, but if I consider this closed surface S2, the situation will be different. If I write the Ampere's law for the closed surface S1, B dot ds is equal to mu 0 times the current, but for the second surface S2, B dot ds will be equal to 0. Why is that? Because for this surface, there is no current flowing through this surface. Okay, so we will have a contradiction here. So this creates a contradiction because Ampere's law says this integral should be equal to mu 0 I enclosed, where I is the total current through any surface bounded by this path P. This surface S1 has the current I going through it. This surface S2, which is also bounded by this path, has no current flowing through it. And Maxwell solved this problem by postulating an additional term, which is called the displacement current. And Maxwell introduced this displacement current, ID, is equal to epsilon 0, permittivity of free space, the rate of change of electric flux, d phi e dt. So if you postulate this current, then the electric flux phi e will be equal to integral E dot dA is the electric flux. Okay. As the capacitor is being charged or discharged, the electric field between the plates may be considered equivalent to a current that acts as a continuation of the current in the wire. So while there is no current flowing through this surface, there is a time-varying electric flux in between the two plates, and Maxwell says that can be considered as a continuation of the current I if we introduce this displacement current. Then what would happen is the closed path integral B dot ds would be equal to mu 0 times the displacement current, because you have this time-varying flux that acts as a displacement current here. So then there is a current going through this surface, which is basically equal to the original current I that flows through the wires. So we obtain the closed path integral B ds is actually mu 0 times the current I plus the displacement current, mu 0 I plus mu 0 epsilon 0 d phi e dt, and that's basically modified Ampere's law, modified by Maxwell, and it's telling that in between the two conductors, this I is 0, you have the displacement current, and in the wire you don't have a displacement current, you have the current I. So this is basically the modified version of Ampere's law. Now if you consider this parallel plate capacitor, which has an electric field in between the two plates sigma, the charge density divided by epsilon zero, permittivity of free space, the electric flux is basically E multiplied by the area of the plates A, which is sigma divided by epsilon zero times the area. Because we have a uniform charge distribution, this would be Q divided by epsilon zero. This is the total charge Q divided by area A. Areas cancel, we obtain Q divided by epsilon zero. Now if I write the rate of change of electric flux, d phi E dt, this is 1 over epsilon 0 dq dt, and that is basically the current I divided by epsilon 0. So I can see that epsilon 0 d phi E dt is equal to the current in the wire that is basically building up this charge. So this is basically the current in the wire. So indeed I see that the displacement current introduced by Maxwell is equal to the current in the wire. The charge stored on the capacitor Q is equal to C times the voltage building up on the capacitor, delta Vc as a function of t. So if I look at dq dt, the current, it is C dvc dt. So the current I, current on a capacitor, is equal to the displacement current, which is C, the rate of change of potential, dvc dt. So this is the displacement current. Okay, so here we have talked about a contradictory situation where if you consider the charging or discharging of a capacitor, where there is a current on the wires that is bringing the charge to the plates of the capacitor, but there is no current in between the wires. If I write Ampere's law as it was given, the closed path integral B ds is equal to mu 0 I enclosed, B dot product with ds, where I is the total current through any surface bounded by this path. If for the surfaces bounded by this path, if I consider surface 1, there is current I. For surface 2, there is no current in between the two wires, so there is no current through this. This creates a contradiction. So for surface 1, it's mu 0 I. For surface 2, it is 0. So this contradiction was solved by Maxwell by postulating an additional term, the displacement current, which is epsilon 0 d phi E dt. If you look at a parallel plate capacitor with uniform charge distribution on the plates of the capacitor, sigma divided by epsilon being the electric field in between the two plates, the electric flux E times the area of the plates is Q over epsilon 0. d phi E dt is 1 over epsilon 0 dq dt, which is the current. dq dt is the current on the wire. So it's epsilon 0 d phi E dt is equal to the current on the wire. So therefore this is basically correct. So when you have a time varying electric flux, you can think of it as an equivalent to a current using this relationship. So with that, Ampere's law is modified. The closed path integral B dot ds is mu 0 times the current on the wire plus the displacement current. So it has two sources, either a time varying electric flux or a steady current on the wire. So it's mu 0 I plus mu 0 epsilon 0 d phi E dt. If I look at the charge stored on the capacitor, Q is equal to C times the voltage on the capacitor. When I take the derivative with respect to time, I see that this displacement current is also equal to C dvc dt, which is also the current on the wire.